Okay, so we are prepared to take a look at the Taylor series expansion. Let's begin by taking a look at the first four terms of the expansion. So the first two actually resolve, the first three kind of resolve nicely. For the first one, and remember in the Taylor series, the very first term was just the function evaluated at the point. So by definition, that would be the zeroth derivative of f of x naught. What would be the zeroth derivative of something? Well, the zeroth derivative is just the function. The zeroth derivative of a function is just the function. And when we're dividing by 0 factorial, by the way, it's kind of weird, right? Because you can think that's 0, but by definition, 0 factorial is actually 1. And now it's multiplied by delta to the 0. And for all intents and purposes, this just means 1. Okay? And so that gives us, when we multiply f of x naught times 1, that just gives us our output at the point. Now, when we do the first derivative of f evaluated at x naught, well, the first derivative of a function with respect to a vector is the gradient. That's the gradient right there. And we're dividing by 1 factorial, which is just 1. And then we have it multiplied by delta to the first, which is just the delta, right? And delta is really just x minus x naught. Okay, now if you wanted to do this as, okay, well, how do you actually multiply this out? Because you have a vector times another vector, right? But this is actually going to be a dot product between them. So what we're going to have is we're going to have the summation of the product of each element inside of the gradient multiplied by each shift, if you will. So imagine what we have inside of here is we have the partial of f with respect to x, and just to do this, illustrate this with two input variables, the derivative with respect to y. Now, then we're going to have, for the delta I, we're just going to have x minus x naught and y minus y naught. And so, and this is of course going to be evaluated at x naught. And this is going to be evaluated at y naught. And so, I'm sorry, at both, I really should say both points. So let me write it like this. F sub x, f sub y evaluated at x naught. And this should be x naught as well here. Because remember, x naught is a vector of inputs, and both partials may or may not depend on those. So what you actually get here is it's the product of the ith element from 1 to a. Now, in our case, a is equal to 2. Because we have two inputs. And remember back up, what was A? Well, A was the number of inputs that we had right here. So A is equal to 2, and it's just going to be the same, right? These are the same locations. So you're going to have, in this case, you'd have f sub x evaluated at x naught times the scalar x minus x0. Now notice we're being very precise here. We're not actually using vectors in this vector anymore because these are the elements of the delta vector. And then you are adding these, so you'd have plus, now that I would go to 2, and it would be the second element times the second element. And that's simple enough to evaluate. So it's like the univariate Taylor series, but you have to have one term for the partial with respect to x and one term with the partial with respect to y. Notice that the gradient is a total derivative vector because it has every partial derivative available. Now, if you move on to the second derivative, of course, what changes is you're dividing by 2 factorial, which is just 2. So division by 2 is the same thing as multiplication by 1/2. Now, the second derivative is the derivative of the gradient vector. Okay, well, what's the derivative of the gradient vector? And I guess I should lay these out horizontally and not vertically, but that's fine. It would be the derivative of x with respect to x, and then the derivative of x with respect to y. Down here, it would be the derivative of y with respect to x and the derivative of y with respect to y. So that would be the Hessian. And then this guy, delta j, remember what that's going to contain, or sorry, the delta squared, what that's going to contain is, if we back up to where we did this, that's going to be this matrix right here. There's delta squared. Okay, so the delta squared matrix would be x minus x naught squared, x minus x naught, y minus y naught, and then y minus y naught times x minus x naught, finally y minus y naught squared. So here, notice what it's saying is that we're going to take, for instance, the 1, 1 matrix, the 1, 1 element of the Hessian, and we're going to multiply that. Well, you could think about it as the 1, 1 element of what the delta squared would look like. Alternatively, this just breaks it apart into the original delta vector, and the original delta vector just contains those two quantities. So this is kind of a shortcut. If we form delta squared first, then it's really just the corresponding product, and then this guy times this guy, and then this guy right here times this guy right here, and then we could say this guy right here times this guy right here. And so again, delta squared is just this definition here. Delta cubed, same kind of process, right? It's just now you have a third layer. All right, let's go ahead and take a look at an example. So this is a function whose derivatives will be pretty neat, because if there are a lot of terms involving combinations or mixtures between x and y, derivatives can be a little bit more cumbersome to find, but we're usually not going to be doing this by hand anyway. So just to illustrate what this would look like, let's take a look at f of xy equals cosine x plus sine y at the point 0, 0. So that's going to be here, and what we want to do is we want to approximate the curvature of this function. So let's go ahead and look at a kind of more of a rotational view of where we are at. So we can see that there's an incline in one direction, but in the other, it looks to be relatively flat, like we're kind of in a max in this direction, where we can kind of see that it's concave down. And then in this direction, it definitely looks like we have a positive rate of change in the direction of y. Okay, so let's begin taking the Taylor series approximation. Now we're going to do this for each of the terms first, and then ultimately we'll look at a third order Taylor series, but we'll actually look at the ascension from a first order up to a third order. So all of the orders are going to involve k equals 0 and k equals 1. Okay, so for k equals 0, first of all, we know that right away that term will just be f of x0. So it's just a function evaluated at our initial point. So in our case, it's going to be f of 0, 0, since that's our point. Cosine of 0 is 1, sine of 0 is 0. So that point right there is just the point 0, 0, 1. Note that this is not an approximation yet, because the 0th term just gets a point. We want a function. So for k equals 1, this is going to be the derivative with respect to x, the first derivative. This is divided by 1 factorial, which is just 1. We already saw that, of the function f of x0. Again, really funky notation here, right? It looks like two things are being multiplied, but it's just the derivative of that multiplied by the delta vector, which in our case is going to be the gradient. Okay, so the gradient of f evaluated at x0 times the delta vector will just be x minus x0, which is x minus 0, and then y minus y0, which is y minus 0. So the gradient vector is going to contain the derivatives with respect to x. The derivative with respect to x of cosine x plus sine y will just be negative sine of x. And the derivative with respect to y of this thing, well, will be 0 plus cosine y, which is just cosine of y. Okay, we still need to evaluate this at the point 0, 0, so we haven't done that yet. I'll just put evaluated at 0, 0, and then multiply by this vector, which just contains x, y. Okay, evaluate this at 0, 0, you'll get 0 and 1 times the vector x, y. This is now a dot product. So remember how I mentioned that we could just multiply corresponding elements? Well, that's exactly what's going to happen when we do a dot product. It'll be 0 times x and 1 times y. So this will just give us 0 times x plus 1 times y, which is just equal to y. Okay, so what does that mean? Well, that means if you wanted the Taylor series approximation up to the first term, you would just take 1 plus y. Okay, so the first order Taylor series approximation, let's go ahead and look at that. I'll write that as the Taylor series first order will be function containing variables x, y, so it's a function. It will just be 1 plus y. It'll be the sum of the 0th term and the first term. Let's take a look at that on the graph. So if I plotted 1 plus y, I have to do z equals 1 plus y. Well, notice that what I'm getting, do this in a different color, is a tangent plane. All we've really come up with the first order approximation. Notice how I mentioned earlier that it's kind of flat. We're at a max, a local max in the x direction, but we have an increasing slope in the y direction. Well, that's exactly the plane that we came up with. So that's the first order Taylor series approximation. Let's go ahead and move on to the second order. So all we have to do there is just to this term, add on the k equals 2. And for k equals 2, this is going to be the second derivative with respect to our vector. So now we're taking the derivative of a vector with respect to a vector. And that means we're now going to get a matrix. So it's this derivative of our second derivative of our function, evaluated at x naught, multiplied by the delta squared vector. Okay, the delta squared vector we've already written out, and it ends up becoming this thing here. So I'm not going to do that again because it's always just going to be, this if you only have 2 variables. Of course, you had 3 variables, well, then you would have a 3 by 3 matrix instead of a 2 by 2 matrix because you'd have 3 functions in the gradient, and then you'd have to take the derivative of each of those with respect to each of the 3 variables, which would give us a 3 by 3. Okay, so if we write that out, so inside of the, and remember this is just the Hessian evaluated at x, 0. So it'll be the derivative of each of our functions with respect to x and then with respect to y. So we can kind of think about this as our first function. Our first function will be in the first row, and our second function will be in the second row, here with respect to x and here with respect to y. So the derivative of f1 with respect to x will be negative cosine of x, and the derivative of that with respect to y will be 0. Function 2, the derivative of cosine y with respect to x is 0, and the derivative of cosine y with respect to y will be negative sine of y. And now we'll need to evaluate that at the point 0, 0. The delta squared matrix, remember all it does is it takes the x and y matrix, vector. This is x minus x naught and y minus y naught, but x naught and y naught are both 0. And it's just going to produce the matrix of the 1, 1 element will be this times itself. The 1, 2 will be the 1 times the 2. And then the 2, 1 will be the second times the first. And then the second times the second will give us y squared. Okay, and how do we multiply these two things together? Well, we want a scalar, right? Because it's just going to be, still the output is just one output. So if we multiply a 2 by 2 times a 2 by 2, well, we get in a little bit of trouble. So I'll reshape these in just a moment. Let's go ahead and plug in our 0, 0. So our 0, 0 here will give us negative cosine of 0, which is negative 1, 0, 0, 0. And then here our second matrix. And I'll just write the component here as xy as well, because if we ever need to add those, we could just combine like terms. And then y squared. Okay, how are we going to multiply these? Well, the way we're going to do them is we're going to reshape these tensors, these matrices, into vectors. So along the first row, that will stack downwards, and along our second row, that will stack downwards. And then we'll do the same thing here. We'll write a dot for a dot product. And all this really does is it just makes it takes away a dimension, right? Because we're still going to multiply the first times the first, the second times the second, the third times the third, the fourth times the fourth, but it's just a little bit easier to do it in vector notation, especially once we get into multivariate matrices, or i.e. officially tensor world. So again, I'll just do the same thing here. Notice I'm not changing the order. It's still the 1, 1 element with the 1, 1 element, the 1, 2 element with the 1, 2 element, the 2, 1 element with the 2, 1 element, and the 2, 2 element with the 2, 2 element. And now I just multiply and add. So negative 1 times x squared is negative x squared. 0 times xy is 0. 0 times xy is 0. 0 times y squared is 0. And that is our k equals 2 term right there. So our second order Taylor series would be t2 of xy equals 1 plus y. And now add that k equals 2 term, which would be minus x squared. Okay, let's go back over here and take a look at what the second order will look like. And ooh, you know what I forgot? I forgot the 1/2. I forgot the 1/2 out here because it's 1/2 times that. And so I want to make sure that I have 1/2. Notice my multiplication concept is a little bit sloppy because we're just using the definition, not actually multiplying matrices here. And then here we'll just have this over 2 or negative 1/2 x squared. So let's do that. 1 plus y, I'll just take the same thing and I'll do minus 1/2 x squared just so we could get the distinction. Okay, there's our tangent plane. Now we get a little bit of curvature. Look at that. Okay, so we're doing pretty good. If you look at that, we are matching the shape, and the way they overlap, yeah, you know, this guy does start to deviate further away as you get below it. You can see there's a gap starting to form, but right there it does a pretty perfect job. In fact, it even does a pretty good job going this way. So let's now get the third order, get a little bit more curvature to it. It's as if what we're doing is we're laying a sheet on top of our original function, right? Imagine you wanted to lay down a sheet. And that sheet, as analogously to using higher order terms, if you're using really low order terms, then that sheet you're laying down is really, imagine it to be really stiff. As you incorporate more terms, you're like reducing the stiffness of that sheet. It's still a little stiff, right? But it's a little pliable now. And when we add the third term, it'll make it even more pliable. And so as we make it more pliable, it should, in theory, start to overlap that function a lot better. Okay, final term, k equals 3. For k equals 3, we should have 1/6 times the third derivative with respect to x of our function, evaluated at the point, multiplied by the delta vector cubed. Okay, let's start with the delta vector cubed. The delta vector cubed, what that will be is it will be our squared delta vector, which was this guy, remember? And it needs to get multiplied by each of the components in the delta vector, right? Because then it wouldn't be a delta cubed, it would just be a delta squared. Remember, this is x minus 0, y minus 0. This is just the delta vector right here. Okay, well, if we're not going to do a strict product, we're going to do what's called, this is actually called an outer product, and it's a little bit weird when you're dealing with tensors, but the first layer for k equal, for the first layer, I'll just say first layer, it'll be all these things multiplied by the first component. Okay, let me do this in a different color so you can see that distinction. So here in the first layer, we'll just have all of these quantities times x. So we'll get x cubed, we'll get x squared y, we'll get x squared y, and we'll get y squared x. Okay, that's the first layer. Now we need to go with the second layer, and the second layer we'll just have times y. Okay, so the second layer, which I'll offset a little bit to kind of give you that element of depth, will be x squared y, then it will be xy squared, and then it will be xy squared, and then y cubed. So that's the second layer, right? Now we're going into tensor world. So this is a 2 by 2 by 2 layers. But what I'm going to do is I'm going to stack everything inside of a vector. I'm going to reshape it. So first layer first, I'll have x cubed, x squared y, going along the rows, x squared y, y squared x. Okay, that's just the first layer reshaped. Now I'm going to reshape the second layer in the same order, x squared y. Remember, we're going along the rows, xy squared, xy squared, and then finally y cubed. And this will make it a lot easier to see how the multiplication takes place, because now with the third derivative, when we reshape that, it'll just be the elements multiplied across and added together. It'll be a straight dot product. So notice that this is now an 8 by 1. 1, 2, 3, 4, 5, 6, 7, 8. You had 4 in the first layer and 4 in the second layer. It'll give us a total of 8 elements. Now I think I'll go ahead and do d cubed off to the side over here just so that we can really visually compare the elements. And what this will require is for us to take the Hessian matrix, which is this one up here, and in the first layer, take the derivative of this with respect to x, and then in the second layer, take its derivative with respect to y. So let me just go ahead and write that. That Hessian was negative cosine x, 0, 0, and negative sine of y. So let's go ahead and take the derivative in the first layer. So the first layer will involve taking the derivative with respect to x. So I'll just say dx, and this will be the first layer. So the derivative with respect to x will be sine of x, 0, 0, and then derivative with respect to x of negative sine of y will also be 0. Now in the second layer, we are going to take the derivative of that same matrix, but with respect to y. So this will be the derivative with respect to y. It'll give us 0, 0, 0, negative cosine of y. And once again, we've done kind of the same thing we did over here. We just have to reshape this. Notice that, again, it's 2 by 2 by 2. And so in the first layer, Now let's evaluate. We also need to evaluate at 0, 0. So let's go ahead and evaluate as we go. So first layer would be sine of 0, which is 0, and then the second 0, which is 0. And then really it's just 0, 0. Not very interesting. Now the second layer. Second layer, 0, 0, 0, 0, and then 0 negative cosine of 0. Well, the negative cosine of 0 is negative 1. And so there is our 8 by 1 vector. Now remember, we got to take 1/6. 1/6 of 1, 2, 3, 4, 5, 6, 7, and then negative 1, dot product with x cubed, x squared y, x squared y, y squared x, all of these elements down to the last one, y cubed. I'm not going to list them all out. Now you can see that the multiplication is going to be pretty straightforward because guess what? They're all going to be zeros until you get to that last element, which will give us negative y cubed. So this will equal 1/6 negative y cubed. And so that will, in this case, be the only term in the third order expansion. So T3 of xy will be 1 plus y minus 1/2 x squared minus 1/6 y cubed. All right, let's go ahead and take our graph and see that this will make that sheet more pliable. 1/6, not going to plot this yet, y cubed. So, progression. We have the tangent plane. No curvature. A little bit of curvature in the second order. Third order, even better. Look at that. Now we actually get a better approximation because it actually bends a little bit more as it goes in the other direction. It doesn't continue moving downwards. But you can still see that, as we move further away from the point 1, 1, or 0, 0, 1, the approximation gets worse. But in the local vicinity, it does a very good job. And that is how we would do a third order expansion. Fourth order, kind of the same thing. What you could do is, if you were ever to do a fourth order, is you could take really just these vectors that are already in third or in the third order expansion, and then to get delta to the fourth, you would just multiply all of these by x, leave that as the first column, and then you'd have another 8 components, and those would be all of these multiplied by y. And now, again, you'd have to take, it gets kind of weird, right? Because now you'd have to take each of these derivatives with respect to x, and then each of these derivatives with respect to y. And once again, you just get another 8 stacks down here, another dot product. It just gets more cumbersome as you go.